So, Chapter 2, Atoms, Elements, Molecules, and Compounds. The chapter is presented as a point of chem study that is the simplest entity that we can start with in the material study of matter. And you recall simply that matter, anything having weight and occupies space, is divided into substances and mixtures. And the category of mixtures evolves to homogeneous and heterogeneous, just to review. And the category of substances into elements and molecules or compounds. And elements are the smallest entity of a substance, having its own personal chemical and physical properties, and are identified by those chemical and physical properties. And the smallest entity of the element is, of course, the atom. And we've learned the origin comes from the Greek atomos, which is essentially indivisible. So this is working our way down to the simplest entity that we know of. And then, just as a repeat for reference, atoms go to, of course, elements, molecules, and we say compounds also, reactions, solids, liquids, and gases, and then solutions, which are mixtures of solids and liquids and all that stuff stirred up. And so this is what we're doing, and this is why we are in this chapter. It is a point at which we can start with something that is simple, something that is fundamentally digestible. So as we begin our study of atoms and elements, we need a definition, and I've already given you that definition, but I'm going to, for the reference, put it back in here. Atoms and elements are the smallest entity of a substance with specific chemical and physical properties, and can not be broken down by ordinary Now, in this definition, they cannot be broken down. Well, that doesn't mean that electrons, this statement applies to gains and loss of electrons in chemical reactivity. What it really refers to is the nuclear stability. All elements, for example, are defined by the number, first of all, by the number of protons in the nucleus. And if you heated up a sample of cobalt or something, you'd have to go almost nuclear before you tear up the nucleus. So that's what we're talking about. Temperatures less than 5,000 degrees Celsius, because it is extremely difficult to pull a nucleus apart and change the element. Now, radioactivity does occur, but that is a far away from what we're talking about right now. Well, we will get into it shortly, but anyway. So now we're studying the simplest entity, and each one of those blocks on the periodic table is an element, and you can go on Google and find quite a bit of information on hydrogen, okay, and helium, and lithium, beryllium, boron, carbon, nitrogen, and on and on and on. And so each one has its own block up there because of its specific chemical and physical properties are different than everybody else on the periodic table. But anyway, when we talk about the structure of atoms, we call that in the community, scientific community, atomic models. And over the history of the development of the atom and an atomic structure, there were 4 atomic models, or atomic theories, that define what the atom looks like. I don't think any of us have seen one. I haven't. But we've seen what that atom is saying to us. Yesterday we looked at that discharge tube yesterday on hydrogen, and the atoms are saying purple to us, okay, and light and energy and things of that nature. Well, the scientists have taken those ideas, and pluses and minuses were actually mentioned in that, taking those ideas and come up with, well, this is what we think the atom looks like, okay. So the first model is called the Thomson plum pudding model. Now, the plum pudding model was based upon the plus-minus attraction of the particles that they knew existed or came from atomic structure. You just see plus-minus electrostatics, opposites attract, like charges repel. But what J.J. Thomson came up with in his analysis, based on the current knowledge of what's going on and what his observations were, was that the atom is a spherically positive charge structure. Didn't have any nucleus in Thomson's structure. And so it had a ball, which he actually showed, that had a concentration of positive charge. And in that distribution of positive charge, if you can see this, you can see where I'm drawing these little dots. These are electrons suspended in that positive environment like plums in a gelatin pudding. And so they didn't know about a proton. So that all they knew was that when a substance was subjected to a high potential, electric potential, it would discharge this green glow and had a negative charge. And they called those electrons in a positive field. Okay, well, that didn't last very long, and there's a lot more information to it. This is just a cursory statement of where we are and where we are going. So the next one is the Rutherford shell model of the atom. This particular experiment, the experimental foundation for the shell model, was called the gold foil experiment. And basically what Dr. Rutherford did is he put a high molecular weight element in a lead container and directed its radiation, something up in the uranium, plutonium, and those high mass will give off radiation in the form of alpha particles. Alpha particle is simply a charged helium nucleus. And they're quite heavy compared to other types of radiation. The electron and gamma rays and those kind of things are almost non-existent weight compared to the structure. This is 2 protons and 2 neutrons hurling through space close to light speed. So when you compare it to other type of subatomic particle structures, this is quite heavy and quite massive. Anyway, so we have these alpha particles being directed at what we call a little thin gold foil sheet. Golf. And this was enclosed in a photo chamber, photo line chamber, photosensitive surface. That is, just to illustrate it, on the inside of this chamber was a photosensitive lining like that. So anyway, what he observed was that, well, one more statement before I tell you what it was observed. The purpose of the gold foil experiment to begin with was to prove the Thomson model. It was understood that it was this big, atoms were this big positive sphere. So before the gold foil experiment, it was assumed that that gold foil had a positive field around it in this context, okay? And what was the expectation? And you should always have an expectation in experimental work. Well, based on the information given, if I shoot an alpha particle, which is also a positive charge, at a surface that's highly positive, what do you expect? It'll bounce off of it like a ping pong ball would bounce off the wall, right? That's what you would expect. Okay, so he sets this up and starts his experiment. This is what they think it is. I'll redraw that. There's the gold foil again. But what they observed in the context of this, is that 99% of the alphas pass through unperturbed. that did anything. That was in total conflict with the Thomson model. It should have reflected all of the positive charges. Now, they did see some minor deflections, and then they saw a very, very small number being reflected or repelled right back at the source. Now, out of that observation came the shell model of the atom. And his conclusions out of this was the atom is not a hazy cloud of positive charge. It consists of two parts. A nucleus and an electron cloud. The nucleus is defined as an indivisible entity of positive charge, and the electron cloud was a diffused cloud around the nucleus having a negative charge. And the significance here, until we get to the more detailed esoteric points of this experiment, is he was the first to propose two-part atom. So that is an easy test question right there. Which of the following scientists was first to propose a two-part atom? And this is why we're at this point. I just wanted to show you the history of how this evolved. So his picture of the atom in 3 dimensions was a diffuse electron cloud having negative charge in 3 dimensions and an indivisible nucleus. So we know today, of course, the nucleus contains certainly can be broken down. Anyway, these would be a diffuse electron cloud. So that's the second model, the shell model. And why it's called the shell model should be somewhat obvious, that it has a dense nucleus and then this shell of electrons around it. So that should give you a visual of what that concept's about. Third model is the Bohr concentric ring model. This one I say you have grown up with for the most part, because it's very applicable to talking about chemistry and chemical reactions and how elements interact by chemical bonding. Well, this was based on exactly what we were looking at yesterday, based on the bright line spectra of hydrogen gas being excited by an electric current, or just simply say based upon bright line spectra. Actually, it's called bright line emission spectra. In which we remember seeing, I told you yesterday, when you look through the spectroscope, you should see a red line, a green line, a blue line, and I don't know if I got any purple in here or not. Yeah, I got one. And a purple line like this. And that's a bright line spectrum of the hydrogen atom. And every element has its own bright line spectrum. And we saw yesterday that each one of these had their specific wavelengths. You don't have to memorize those. If I want to give you a problem, I would certainly give you those. Blue and violet, just to emphasize the point I'm making. This was 656.8 nanometers. Another one was 486 nanometers. Then 433 nanometers. And 410.1 nanometers. Of course, a nanometer is what? 10 to the minus 9th meter. Meters being that meter stick up here, so it's itty bitty. At any rate, what does this tell us? And we showed you yesterday that what it tells you is that in a typical atom, this is his conclusion. In a typical atom, according to Bohr, this was his conclusions. The atom consists of energy levels in which the electron lives. Nucleus and electron energy levels. And if we're looking at hydrogen, and we have learned, and I mentioned it yesterday, we have learned that hydrogen consists of one proton, one electron. And if you were asked to draw a picture of it, you'd probably draw your proton and draw some concentric ring around it and put your electron there, right? Well, what I want you to see out of this is that when the electron is in the first ring, or n equal 1, that's the designation for energy levels. Lowercase n is what we call the principal quantum number. But just understand the next one would be n equal 2, and second energy level. These were then invented, so to speak, because of this. It was understood that the atom now is not just a dot and a fixed orbit of an electron at a certain distance, like the moon orbits the Earth. That electron is very active. It moves from this point outward and back in. Okay? When it's going out, that's called an absorption spectrum. When it's dropping back toward, as an emission spectrum. The terms are somewhat definitive. This is an emission spectrum. And emission of what? It's the energies, like I showed you when I dropped the pen or the chalk yesterday, and that chalk gave off some energy, right? But the potential energy was changed from high to low. Well, the energy left is kinetic energy. Well, that's a mechanical. But in quantum material, and there's a lot of interesting stuff in my humble opinion, the electron in a higher energy point, like n equal 2, n equal 3, n equal 4, and so forth, like that, when it falls back down, gives off its potential energy and turns it into electromagnetic energy, and we see it as light. And so the outcome of this was the electrons live in individual rings. Now, one of the interesting things, and this in passing, we'll develop this in more detail in chapter 7, is that when an electron is in a given ring, say you have it in n equal 1, 2, 3, 4, n equal 4 ring right here, and then all of a sudden it gives off light and you find it in n equal 2 ring. It's interesting to note that this drop is a specific loss of energy, a discrete loss of energy. Now that's abstract at the moment, but what does that mean? when an electron transitions from, say, 4 down to 2, it's going to give off this green line. It's not a hazy green line. It's not a smeared green line. It's very, very fine line, which has a very specific wavelength of 486 nanometers. That's called a discrete energy transition or quantumization. That's what quantum is. It gives off a very specific energy value. If the point of contrast, if the electron stopped in the middle somewhere, you see the entire rainbow that you looked at through the spectroscope yesterday. You see the whole thing. But that's not what you see when you look through the spectroscope. You see specific colors. Those specific colors mean the electron's in number 4 or number 2, but it ain't between them. It just disappears out of 4 and shows up in 2, and then nobody in the middle noticed it. So that's the point I'm trying to make, in that the conclusions for the concentric ring model says, well, the electron's going to be in ring 1. When you fill up that one, you start putting them in ring 2 and ring 3. So we ultimately come up with the concentric ring model, n equal 1, n equal 2, 3, 4, 5, 6, and 7. Like that. And if we got a stack of electrons over here, we start putting those electrons in. We fill up that one, then we put in a bunch in here, fill up that one, and we put a bunch in that one. And experimental evidence showed that structure of the atom. And so that's where the concentric ring model came from. And it is used extensively still today. It is excellent, especially when you show the element and the outer shell. That's called a Lewis structure, and it shows the gains and loss of electrons in the reactive process. And it's very useful. It's a little more cumbersome when you get over into the next model of the atom, which is the 4th one. This is the last point in your history lesson here. And it's the 4th model is what we call the Schrodinger quantum model. The Schrodinger quantum model is what we call also the modern quantum model, or the model atomic model. And this one is based upon the wave particle duality of the electron. In some analyses, the electron is treated as a particle. A Newtonian particle is what it's called. An individual entity, a BB flying around the nucleus. In some analyses, it's considered a wave function. It acts as an electromagnetic wave, like light, floating through the void of the universe. And so that's what we mean by wave particle duality. Well, what's the significance of this? If electron analyzed, I don't want to spell analyzed. Analyzed is a wave that leads to quantum mechanics. This is the study of electron behavior in terms of probability and statistics. And the application of that from a mathematical standpoint is called wave mechanics. Well, what it leads to are quantum numbers. And there are 4 quantum numbers spelling the word palms, like cheerleader pom-poms. Okay? P-O-M-S. Real easy to remember. There's a principal quantum number given the designation N, an orbital quantum number given the designation L, a magnetic quantum number given the designation M, and a spin quantum number, M sub s. Every electron that orbits an atom has its own set of 4 quantum numbers that is different from any other any other electron orbiting that even the same nucleus. Now, what's the significance of that? The significance is that the electrons don't bump into one another. Think about uranium, number 92. You got 92 electrons buzzing around that nucleus at light speed, but nobody bumps into one another. This set of quantum numbers, N, L, M, M sub s, for a given electron, separates it from all the other electrons. They call it the quantum window. N, L, M, and M sub s assigned to a given electron says that no other electron can live inside that window. And it has its own place in the three-dimensional space that it exists in. And those are called electronic orbitals. And you've seen those maybe in earlier courses in the form of the shapes S, P, D, F orbitals. And you have used these in what we call electron configurations. That's where these things came from. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and it just goes on and on and on for a given element. I'll show you how to do that when we get there, proper time. But that's what this is. That's what all of the quantum mechanics leads to, is defining the electronic configuration from. So now I've given you a sketch of 4 models or pictures of the atom. One starts here, and then Rutherford comes along and says it's a shell with a nucleus, and then the Bohr model comes along and it's got rings around it, and now we have the Schrodinger model, and in some cases you see those like that. And people have defined the atom like that, and so we see these 4 models evolving out of the history of studying the atomic structure.
So what was the...
Okay. The topic is atomic structure from the periodic table. When you look at the periodic table, I'm sorry about the imperfection in the printing, but when you look at it, each one of these element blocks in here is separated from another element block because each one of the elements has their own physical and chemical properties. Now, in the element block, you have 3 items in here, what we call an atomic number, the element symbol, and the atomic mass, right here. And so we will use this information in here to determine how many protons, electrons, and neutrons exist within a given element. So we'll start with oxygen. Say that's easy enough. Give me a second. Okay. So this is the element block, and you'll have periodic tables that have of course a lot more information in each block, than what I'm showing you, but this is what you will get for test day. Now, the elements are arranged by chronological order, 1, 2, 3, 4, all the way up to 100 and some odd that we know about. And this is referred to as the atomic number. And it's given a designation in the literature as a Z number. The charge number is what it really is. The number that's 15.9994 is called the atomic mass number, and is given a designation capital A. Now, one of the things you need to understand about this information is that the atomic mass is the sum of proton weights plus neutron weights. Protons being designated P with a little plus is what I'll use, and neutrons in neutral as given in that. Now, the first thing in first relationship in this is your atomic number. That is the number of protons. So when we talk about the arrangement of the elements on the periodic table, it gives rise to what we call the periodic law. And that states the chemical and physical properties of the elements are a periodic function of atomic number. That is, number of protons. If you change the number of protons on a given element, you change the element. Oxygen has 8 protons. Take out a proton, now you've got nitrogen. So it's very important that you understand that up front about the nature of elements. Say, given the atomic number to be, say, 8 and atomic mass to be 15.9994, there will be other unit applications here, but for right now, the atomic mass is going to be an AMU value. That means atomic mass units. That's what the AM is designated for. Now, for oxygen, you're given this information. So the question is, how many protons and neutrons exist within this structure? Like that. Well, from the atomic number, we get the number of protons, and in this case, 8. 8 protons are a part of oxygen. The number of neutrons comes from the idea that the mass is equal to the number of protons plus the number of neutrons. So we can determine the number of neutrons from subtracting protons from both sides we get the mass, the number of neutrons to equal the mass number minus the number of protons. Now, for estimation point of view here, it is assumed that these just simply have 1 AMU mass for each one of these, a neutron and proton. So if it has 8 protons, that means it has an 8 mass number, AMU. Okay? So the only one that we haven't defined is the neutron. Well, you're given a mass up here of 15.9994. For the purpose of defining, say, an absolute amount of neutrons and protons, round that number to the nearest whole number. Round up on the mass. So mass given to be 15.9994, what you do is just change it to a 16. Okay? And then you can subtract the number of protons minus 8 protons, and you would get 8 neutrons, like that. And it's a simple deduction right there. Now, it's easier to remember if you understand the symbolic designations that are associated with each element. Oxygen, or any element, let me do it this way, any element, say X, is a symbol, will have its atomic mass number as a superscript left, and its proton number as a subscript left, like that. So applying this convention to oxygen, we have 16, big O for oxygen, and 8 for the number of protons. So this is the neutrons plus protons. And this one is the number of protons. So to get the number of neutrons, big number minus the little number gives you 8 neutrons. And this is true for all designations of elements. For example, let's go up here. We'll just pick a few and see how we can do with neutrons and protons. We'll get to the electrons in a moment. Okay, so element, I'll just pick some. Let's go to magnesium. Magnesium. Okay, given magnesium, we see its mass number, if you can see this on the here, but you have table number 12 on here is 24.305. So we'd round that to a mass number of 24. Also, note that sometimes the mass numbers are above the element and the atomic numbers below the element or to the side of it and top of it. Different periodic publishers will put this data in various places, but you know that the elements are arranged by atomic numbers, 1, 2, 3, 4, 5. But it's easier to define at least the mass and the atomic numbers and the symbols. Well, magnesium is number 12, so if you'll set it up like this, then the number of protons and the number of neutrons are pretty easy to define. This, of course, would be 12, and then you would have 12 neutrons. Calcium, which is 40 and over 20. And, of course, that gives you 20 protons and 20 neutrons. Now, up until about element number 20, the proton-neutron numbers are equal. But beyond that, we find a divergence occurring between the neutron numbers and the proton numbers. It kind of goes up to atomic number 20. You'll see an asymptotic neutron number like that. And here's your asymptotic line. But you'll start seeing a diversion from that as you get past calcium. And for example, if we go to iron, we can go here to iron number 26. And we'll look at 56 as the mass number. We just have 26 protons, but we have, you see how it's starting to converge diverge away from the asymptotic relationship or the line. This increase in neutrons is to hold the nucleus together. Now that, of course, is a nuclear issue, and that we'll cover that in second semester in chapter 20, somewhere in there. But and neutrons begin to increase, and you get up into the uraniums, for example. Here's 92 atomic number, and the most abundant one is 238, element 238. So I have to calculate this every time I do it. So we're looking at 146 neutrons for just 92 protons. So in the context of, well, the massive number of neutrons is there to hold the nucleus together. That's all you need right now. Okay, and how it does it's another story. This kind of thing. Anyway, well, what about electrons? If I put electrons on this, I'm going to cover this space over here. The electron numbers will equal the number of protons for a neutral element. That is, the number of plus charges must equal the number of negative charges, and we call that a neutral element, right? I think you understand that idea. Now, for chemistry, chemical reactions and the interactions of elements, you're going to have gains and losses of electrons, which evolve to ions. The definition of ion is charged particle. So the idea is gains and loss of electrons will make ions. So we'll deal with that shortly. But for right now, we're going to say, okay, what's as an orientation to this, what are the number of electrons a given element has? Well, right now we're going to say it's a neutral element. And you'll find a designation many times where people will put a little circle as a superscript right on the element, and would be understood in the community to be a neutral element. That is, the number of protons equals the number of electrons. Now, if I came up here with magnesium and put a +2 up there, that means it lost 2 electrons and has a positive charge. Now, you can't gain or lose protons, right? Because that defines the element. So that's what, we'll get to that in more detail in a few minutes. So if you have the number of protons, you also have the number of electrons associated with that element. So that's a quickie understanding. So if you understand the notations here, you can figure out protons, neutrons, electrons. One other notation on elements, and it's kind of is like this. I'm going to come down here and do magnesium. You'll see magnesium, that what we've shown is 2412 neutral, but it's also listed as magnesium dash 24, like that. And it doesn't have the 12 on it. Well, regardless, all of magnesium elements will have 12 protons in them. It doesn't matter what the nuclear structure is. We're talking about isotopes now. Because some magnesiums have 12 neutrons and 12 protons, but some of them, a smaller percentage, have 12 neutrons and 12 protons and 13 neutrons, or 14 neutrons, okay? And that comes into here, into the mass number. So neutrons affect mass number. But one thing that's always true for a given element is its atomic number. It's always 12. You change the number of protons, you change the element. If you have magnesium with 12 protons, and all of a sudden you reach in and yank one out, so that goes to sodium. So if you look on the periodic table, there's sodium right next to magnesium, one less proton. So no matter how you write this, if you put the magnesium symbol and then the mass number out here, everybody understands it's still got 12 protons, like that. Okay, variations in atomic structure, isotopes and ions. Isotopes are variations in the nucleus. So nuclear variations, isotopes, deal with nuclear variations. And ions deal with electronic variations. And typically that's a variation in numbers of electrons. And here nuclear variations are variations in the numbers of neutrons. And so that gives rise to the isotope issue. So we begin with isotopes. These are a set of elements all having the same atomic number but different atomic mass. And due to numbers of neutrons. So there's a variation in neutrons. So you can't change protons, but you can change neutrons in here. So that's what this handout is supposed to show you in terms of how that affects the mass of the elements. So if we look at this handout, we see that the isotope is called oxygen-16, oxygen-17, and oxygen-18. All have the same number of protons. They all have 8 protons, but they have, this one has 8 neutrons, 17 has 9 neutrons, and 18 has 10 neutrons. Okay? So that's what the idea is here, is to identify, well, you can vary the number of neutrons in the nucleus, but you can't vary the number of protons. Now, out of that, we can take a mixture of all of the oxygen samples in the universe and run them through what is called a mass spectrometer. And what that does is it separates a mix into a mixture of isotopes into their specific isotopes by mass. So that's what a mass spectrometer does. Essentially, to make it kind of understandable here, you have a machine over here. There's an ionization chamber, and you have a negative plate here on this. Well, actually, you have a positive and negative plate. And the elements, isotopes, set of isotopes are ionized and ejected out here. And it's like a sports car throwing a ping pong ball out a window and a brick out of a window with the same speed, starting at the same speed. Well, who's going to go the farthest? The lighter one or the heavier one? The heavier ones will go further because they have more momentum. So what happens is this, these become positive in the ionization chamber, and so you have the heavier isotopes, say oxygen-18 here, and then you'll have a collection of oxygen-17 there, and then you'll have the oxygen-16. And these are by the instrumental analysis related to the percent abundance of those. They got a chart on there, and it gives you a little line that says, well, this is 85%, and this one's 22%, and this, you know, like that, or 20% or something. At any rate, that's what we call fractional abundance. That's the decimal fraction or percent abundance. So when you look at the handout that I've given you here, these are percent abundances. And the fractional abundance would just simply be moving the decimal 2 places to the left. Now you'll need the fractional abundance to do what I'm about to show you. So bear with me a second. Move this up here. So in this relationship, what I want to do is get the weight average contribution of the oxygen isotopes to the overall mass of all of the oxygen in the universe. It's called a weight average contribution of isotope to mass of set. That's the best I can give you right there. That means that what you want to do is take the fraction, the weight average contribution, weight average in short, is the fractional abundance times the isotopic mass. That's where this is all about. What this is all about is how these relate to the periodic table. And it turns out that the sum of all the weight averages, weight average contributions, is equal to the atomic mass on the periodic chart. And that's what the purpose of this little handout is, to show you how it matches that. Now you can look these up on Google or wherever. So we're going to take isotope, oxygen 16, oxygen 17, oxygen 18. Its fractional abundance 0.99759, and this one's 0.00037, and this one is 0.00204. That is that many per 100 or something like that. And then the isotopic mass is 159949. That is not a typo. And this is atomic mass units. 1699.91 and 17.9992. Put that out of the way. Okay. Weight average and atomic mass units is what. To get that, it's the product of those, the fractional abundance times the mass of the isotope. So I just set it up like that. Once you get the list, you just convert it to a decimal in here if it's given in percentages, and just multiply the mass times the given times that, and the fractional abundance, and you'll get a number over here. And then what you want to do is add those numbers together, and you'll get the atomic mass that's on the periodic table. So hopefully that's easy enough. And of course, I will give you one like this or a different element on exam day. So it's pretty straight. Okay, so those are the weight average contributions of the given isotope to the overall total mass of all the isotopes. So the sum of the weight average contributions is equal to the sum of those three numbers. So when we add that set of numbers together, that's where we get the total weight average of all the isotopes. And this is the mass value published on periodic table. Well, you can do this for any element. You can go on Google and Wikipedia and find out what isotopes exist for a given element, and it'll tell you the fractional abundance and the isotopic mass, and you can confirm what I've just shown you or not. And it's pretty straightforward calculation. Now on test day, I'll just give you the same data, but for a different element. And so you just have to remember fractional abundance times the isotopic mass, and then add up all the weight average contributions. Okay, so the next topic is variations in electronic structure. So just to review a moment, remember we've got a nucleus, and the maximum number of rings we know of is 7. If you'll look on the periodic chart, how many rows do you see on the periodic chart? There's 1, 2, 3, 4, 5, 6, 7. Elements in the row 1 have 1 ring around them. Elements in row 2 have 2 rings around them. Elements in row 3 have 3 rings around them. See, that's pretty simple, right? Everybody hear me? Okay, so we always start with, of course, the hydrogen level issue, and we fill up the first ring, and then we go, if the elements in the second, then you put electrons in the ring in the second level, and then if you have an element in the third row, it's going to have elements it'll have electrons in the first ring, second ring, and third ring. So any element you pick out, you can, just go across the chart, you know how many rings it's got, or energy levels is really what I should be saying, but a ring seems to stick better. Each of these energy levels are designated by an N number. 1, then N equal 2, 3, 4, 5, 6, and 7. The rings inside the last ring are called the core structure. And many of you have heard, let me put the 6 in there. And the last ring in the electronic structure, the last energy level, is called the valence level. Now, the core structure for your present knowledge and your knowledge level and learning curve is unreactive. It's stable and unreactive. So you don't gain and lose electrons out of the core structure anywhere. The valence level is where, listen, all chemistry takes place. So all chemical reactions are associated with gains and losses of electrons from that valence shell. So it's important that you understand some elements have a greater tendency to lose electrons, while some of them have a greater tendency to gain electrons. And how do you tell this from what's on the periodic chart? And they call it periodic trends. Is the generalization that's used to describe how the properties of the elements change going from left to right or from top down on a periodic chart. Now, these rows on the periodic chart are referred to as periods or series. The first row is the first period or first series, and it contains hydrogen and helium. Then you go to row 2, which you recognize has 2 rings around it, and of course that is lithium, beryllium, boron, carbon, nitrogen, fluorine, blah, blah, and you rattle them off if you want to. The vertical columns on here are called groups or families. Hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, and so forth, vertically. So columns are called families of elements or groups. Like that. Now, some of these groups have specific names. If you look at the top of your periodic table that I gave you, you'll see a 1A and a 2A designation. Then it jumps over to 3A, 4A, 5, 6, 7, and 8. 8 doesn't have a designation. Some people put an A on there and some people do not. But the groups that are listed in blue over here shown are called the main group elements. All those columns in the blue are main group elements. So you can come in here and say groups 1A through 8A are defined as the main group elements. We'll talk more about why they're as they are. Now, if you look at the chart and you see in the middle, you can block these off on your diagram. I don't have it in color. I can't afford color printers. Anyway, this is called the transition elements. This collection in here. So the groups, they're sometimes they have designation groups between the main group elements, or B groups. Many of the charts will list the designation as 1B, 2B, 3B, and so forth like that. And I just, for our purposes right now, we'll just call them B groups. These are referred to as the transitions metals. Okay, and that collection in the pink in my chart. Then at the bottom, you have a group that kind of evolves out of the transitions. Notice it starts at number 58 in this example here. You can't see it right there. And then the second one starts at 90. Notice that it is, here's 57 right here, and then they pull this row out of the periodic table. So right here, the green set of elements has been extracted and put down here. These are referred as the inner ER transition elements. And they would be inserted right in here. And there are reasons for doing that, including make the chart more usable. If you put them in, it stretches the chart out to the wall over there. At any rate, this is called the lanthanide series. I can't. And this is, you see AC on number 89. This is actinide. The actinides are actinide series. But at any rate, there are certain characteristics of that are common to all of those elements, and we'll get to those in due time. Okay, so we have main groups, and you have this included in your main group. And groups 1, 2, and there's a block over here, and then you have your transitions and your intertransitions. Well, all of these are, let's see, then your intertransitions. The lanthanides and actinides. Now, in the main group elements, certain groups have names, what they call official names of a set of elements in a group. And these include group 1A, group 2A, group 7A, and group 8A, the noble gases. The other groups do not have formal names, but we call them something, and I'll show you that in a second, why they're as they are. But group 1A is lithium, sodium, potassium, rubidium, cesium, and francium. Now you'll have the periodic chart in front of you on your test. So you can pick out a group 1 element or group 2 elements, or your beryllium, magnesium, cesium, calcium, strontium, barium, and radium. And group 3 are over here, but here's group 7 that has a name, and group 8. And those names include, this is the alkali metals. That's your group 1, excluding hydrogen. Hydrogen is typically not included in the context of being an alkali metal. It's not a metal. All right. Then group 2 has 2 words. It's alkali earth metals. And then you jump over to group 7. Very important. Now don't lose this one. People handle group 1 and 2 and then they'll fall off with number 7. Group 7 is called the halogens. Fluoride, chloride, bromide, and iodide. Acetine is not typically listed in this collection because it's what we refer to as a metalloid, and I'll show you that in a minute. That's the last designations. And then, of course, you have the noble gases. That are listed on here, the helium, neon, argon, krypton, xenon, and of course radium. And then you have ununanium, which we're not going to like that. But since you have the periodic table, you should be able to pick them out without any trouble. Now the other designations do not have formal names. The reason is the transition between non-metals and metals. See this little staircase right here? So on your periodic table that I gave you, start on the left of boron and draw a little staircase like this. And you can bring it all the way down to the base of the periodic table if you would. Now, in general, there are 3 classifications of elements: metals, nonmetals, and metalloids. Now these are subcategorized, but we're looking at metals, metalloids. I'll put them in this order for a reason. Oops, I need to bring that down. I'm sorry. Metalloids and nonmetals. when we starting with the metalloids, see this staircase designation, if an element block touches that, the walls of that staircase, it's classified as a metalloid element. Like that, and don't consider that one. So these particular elements that are double marked there are referred to as metalloids. That's what this is. The non-metals are all of the elements back over here to the right of the metalloids. So this collection in here is your non-metals. Okay, and when you get to the left of the metalloids over here, these are including the pink and the green and some of the blue down here, and the other left column, these are all metals in the general classification categories, including these here. Okay, so metals, metalloids, and so what have we learned? Well, when you look at the periodic table, it's divided into what? Rows, series, and periods, columns, groups, and families, groups of elements, metals, nonmetals, metalloids, like that. They have designations of main group elements. They have designations of transitions, intertransitions. All of this you need to learn. As we go through the course, you will be understanding more about the properties and why elements are categorized in those designations, so that hopefully, at the proper point in the course, it will make more sense as to what we have. But one of the questions I posed a moment ago is why do groups 3, 4, and 5, and 6 not have formal names? Because of this staircase and the transition as they move, as the element series or groups move through the change through the metalloids, it goes from non-metal properties to metallic properties. And so the issue with groups is that everybody in the, say, the halogen group, fluoride, chloride, bromide, and iodide, acetine including, all have the same kind of chemical physical properties. Now, some react faster than others in the process, but they all consistently have the same properties. Same way with groups 1 and 2 and of course 8. They all have the same kind of properties due to their reactivities and their chemistry and their physics. Well, what does the reactivity depend on? That's when we get into the variations in the electronic structure. So variations in electronic structure are responsible for variations in chemical and physical properties. So that's what is leading, that's why I gave you all this pragmatic information leading up to this point of, well, what accounts for the properties and the reactivity of the elements? What are the periodic trends in the elements and how they gain and lose electrons and react with other substances? All right, look.